So last time I realized I went a little too fast and I introduced too many things at once. So I refactored lecture 12. So let's start at the beginning of lecture 12. Of course, I erased everything, so I have to make it regular. I just want to run the first two levels of lecture 12. Everything else will be things that you've seen already. So you have some function, you have some a function from n to itself. In other words, well, we're trying to construct a subsequence out of the fact that sigma always stays above n. Okay, so let me write this down. So this is the iterated subsequence lemma. So here's a little warm-up. This is maybe warm-up one. Warm-up one theorem. We're given a sequence. Well, we're given a sequence of natural numbers. We're given some base point n0, and we're given the fact that this is called h sigma, that for all n, sigma of n is at least n. So this was the situation we saw last time where whatever this thing is doing, it can't go below, it's not monotonic, but it can't go below y equals x. The graph of sigma can't go below y equals x. Okay, and well, sigma is not monotonic, but there is a way to get a monotonic subsequence out of sigma. And the idea is to use orbits, right? Exactly as we saw last time. So the goal is to show that the function that maps n to sigma to the n, starting at any base point like n0. So I just start somewhere, n0. n0 is any starting point. Here's sigma of n0. Well, sigma of n0 is greater than n. So that's over here somewhere. That's sigma of n0. And then what is sigma of that? Well, that's greater than sigma of n0 is greater than sigma of n0, and so on. So we want to show that this sequence is a subsequence. Okay, strictly increasing. How would we do it? So what does it mean to be a subsequence? Recall, I'll say tau is a subsequence or satisfies subsequence if Joe. Yep. Yeah. I guess tau here. Yeah, exactly. Yeah, if I is less than j, then tau of I is less than tau of j. Okay, we want strictly increasing. Now, this is an annoying thing to deal with when you have iteration, because now you want to go from any I and any j. This is actually the opposite of what we just saw with Cauchy sequences, and whether it's enough to look at the successor of a Cauchy sequence to know know that this tau is a subsequence. It's enough to know it just from one term to the next, just by induction on the natural numbers, to know tau of n is strictly less than tau of n plus 1. Unlike Cauchy. For Cauchy, it's not enough to know that the difference between any two consecutive terms is small, because that can accumulate over time. But for monotonicity, it is enough to know that if tau of n is strictly less than tau of n plus 1, then whatever tau is doing, it has to be strictly increased. That's a theorem. So I'll click on show me more help so that we don't have to look at what the theorem is. That theorem is called subseq of suc. Okay, so there's a new theorem. It's called something is a subsequence if you checked it on the successor only. And what this theorem says is tau of n is less than tau of n plus 1 for all n implies that subseq tau. Does that make sense? Now, we haven't used the full power of the apply tactic yet. So let's learn about power of the apply tactic. The hint says, start your proof with apply this theorem. So our goal says something is a subsequence. And this theorem, subsequence of successors, says, if you can show that you increase from n to n plus 1, then that gives you subsequence. So when you say, so your first line, if you start with apply this theorem, subsequence of successor, what it will do is it will say, what is the conclusion of that theorem? The conclusion of that theorem is that something is a subsequence, and our goal is that something is a subsequence. So it'll match those two and say, oh, so what you mean is it's enough to, if we apply this theorem, then it's enough to show it from n to n plus 1, that we increase from n to n plus 1. Okay, does that make sense? So we've been using apply like exact, but apply actually has a lot more operability. So let's try apply subseq of successor, and the goal is turned into for all n, and you see why this would be a more convenient thing to do if you're doing iteration. For all n, sigma to the n of n0 is strictly less than sigma to the n plus 1 of n0. That's the new goal. Does that make sense? Why that happened? Okay. So after this, our new goal is this, for all n, sigma to the n of our base point n0. Maybe I should have used a different letter so that the n and the n0 don't look too similar, whatever, is strictly less than sigma to the n plus 1 of our base point n0. So how do we start that? Intro. Yep, we have a for all n, so we intro n. Now our goal is this. How are we going to make progress on this? Remember what we have. The only thing we know is that sigma of n is always strictly greater than n itself. Jeffrey. Yeah, it was iterate. Let's see. I don't remember the name of the theorem either. So the theorem that we had was successor iterate. Successor iterate. Right. So there's a theorem, I'll recall that we have a theorem called the successor iterate, which says that sigma of sigma to the n of anything is equal to sigma to the n plus 1. Okay. On the right, it's by definition. So in parentheses, by definition, this thing is equal to sigma to the n of sigma. So the way iteration is defined is you just iterate, I don't know what this means, on the inside, whereas this is iterating on the outside. Okay, so our goal is to prove this. So how do we want to turn this sigma of n plus 1 into a sigma of sigma to the n. So that's Sean, rewrite. And what do we want to show? Exactly, of n0 is equal to sigma to the n plus 1 of n0. And why is that true? By apply this theorem, suc iterate, the successor of iteration. Here's the problem. Remember, with a rewrite, you look at the left-hand side. And it's not going to find sigma of sigma to the n. Sean. So you do a backwards rewrite. If we backwards rewrite, then it's going to look on the left-hand side. It will find that. And the new goal will be to show that sigma to the n of n0 is less than sigma of sigma to the n of n0. And why is that true? Let me go back to here. Other than Jeffrey, John. Exactly. Apply H sigma. So apply H sigma. Okay, does that make sense? Jeff.
Wait, for the rest then, because I think I did it differently when I was like selecting the level.
Yeah.
Why can you not just do like rewrite the left arrow and then like select it?
You can.
I'm pretty sure that's what I did.
You can, and it does work. I'm trying to discourage you from doing naked rewrites. So naked applications of tactics where you don't specify what you want the tactic to do exactly. So when you say rewrite left arrow suc iterate, it does exactly what we're telling it to do, but it does it under the hood. And for pedagogical reasons, I want it not under the hood. I wanted to expose what that theorem is accomplishing. So you're absolutely right. And in fact, when we do it, let's do it the slicker way, which is just to rewrite backwards by suck iterate, but not technically, but pedagogically, I would like you to do this so that if you're, let's say you called the wrong theorem or something, I still understand what you were trying to accomplish. Does that make sense? All right, so that should do it. Let's try, so we applied this subsequence of successor. So now we have to check the increase from n to n plus 1. We have this. We can do the slick thing, rewrite left by suck iterate. And of course, lean knows what that means, so it'll do it for us. Is that too small? Can you see that in the back, Brandon? It's okay. And then we apply H sigma. And again, we don't have to specify what value. I mean, the perfect solution would be H sigma of sigma to the n of n0. But in fact, apply will figure that out. If I retry this last level, apply will figure that out. I would prefer that you put it, but lean will figure it out. Okay, any questions on that? Okay. I would rather you always specify what you want that rewrite to, what you think that rewrite is doing. There are some where it's not a rewrite, like field simp. It's something where everything is moving, and so you can't do it. But otherwise, yeah. If you're doing a rewrite, I think rewrite show what you're trying to rewrite by, and then that's a good pattern, good pedagogical pattern. John.
Not like this make sense and stuff, or
That's field simp is one where there's kind of no way to put clothes on it, to dress it. Just because it's not rewriting, it's completely changing what the equation was. Like I'm cross multiplying by denominators and stuff. So maybe you could do show, and maybe you could just do show, and then here's what the new goal should be by field simp. Actually, that's I should have thought of that. Yeah, that's a way to dress it up. Thank you. Show is not a temporary have. Show is like it's making explicit what's supposed to be happening. So it's not really a have. Like let me try to give you an example. If your goal is m over n is equal to or is less than epsilon or something, if that's your goal, then you can write show m is less than epsilon times n by field simp. I think this should work. And then the goal will change to m is less than epsilon times n. So you see what's happening when we do one of these big rewrites is we're creating it's like a have. We're creating a sub goal. The sub goal is this. The solution to that sub goal is this. And then we're immediately rewriting it without naming it. So that's why that works. Does that make sense? Yeah, I think that's a better way to use field simp. You should say what you want the answer to be. I don't know how robust it is. We'll have to experiment. Okay, any questions? Next level. So that's the technique that I should have introduced before, because I think I threw too many things at once at you. There's another technique that I wanted to introduce to you. One was about orbits. We talked about orbits. The other one was about a more enhanced usage of the choose tactic. So let's say you're trying to prove the twin prime conjecture. Okay, and P is the property that says yes or no whether the number n is a twin prime. In other words, n is prime and n plus 2 is also prime. And so the statement of the twin prime conjecture is, well, there are arbitrarily large twin primes. So for all natural numbers n, there's some little n greater than that, capital N, for which n is a twin prime. Okay, you could imagine that kind of statement. Of course, we have these all over the place, having nothing to do with twin primes. We have it all over the place in real analysis. And so when you write choose, I mean, we saw, again, I'm teaching something that we already saw last time, but we saw it in the middle of a proof, and I want to isolate this behavior. So what I want is a sigma, which is a subsequence, so that along this subsequence, the property always holds. We have an abstract property. We just have some map from the natural numbers to prop, and we have a hypothesis that there's always, no matter how far out you go, there's always some other number that satisfies that property. So can you recover for me the subsequence, which not necessarily has every number with that property, but any number that you do land on is a number with that property. Does that make sense? What this is asking? Let me try to write it down. So next theorem. So we're given our objects. We have a property, which is just a function to prop. Okay, for any natural number, I can tell you yes or no. And we have the hypothesis that there are unbounded, the set, I would say in natural language, the set of n for which the property holds, P of n holds, is unbounded. i.e., for any natural number, no matter how large, there's always some number past that number for which P of n holds. Okay, and the goal is to produce a subsequence along which, let's call it sigma, along which P of sigma of n always holds. Okay? Does that make sense? So what's the first thing we should do? John's got an idea. Sean's got an idea. Daniel?
Choose the goal. And have it like change the goal to true.
You can't choose using the goal because the goal wants to know that there exists some sigma. We don't have the fact that sigma exists.
Can you say that like this is the same as that implies true? Like this is an H. Can you say like H is the same, or okay, it was H2. If the goal is H2.
But the goal isn't H2. That's the problem. Saying the goal is H2 means that you have the goal.
Or I'm saying, wouldn't it be equivalent to saying that, like, I'm not saying say that we have H2. I'm saying just call the goal.
Call the goal H2, go on.
Great. Is that not equivalent to saying H2 implies true? No. Just like if I had a not that, it would be the same with H2 implies false.
But in order to give me that H2 in the first place,
You know, like backwards truth, right, when false implies that kind of thing. Like, even if H2 is false, like the statement H2 implies true, but still.
It's still
Oh,
true.
that's a good point. Okay, yeah, I didn't.
Good question. Other questions or suggestions for what to do? Where are we supposed to get this subsequence from? John? From H, and how do we get it from H?
Let's choose for, we choose, I don't know, is it like choose tau?
Yeah, we're supposed to do choose when there's a there exists there, but this is a for all. But you can do choose on a for all if what comes after it is there exists. So in other words, really little n is a function of capital N. So give me that function, give me a proof that little n is greater than capital N, little n of capital N is greater than capital N, and give me a proof that P of capital, little n of capital N holds. So that's what this more help thing is. Start your proof. So when we write step 1, we'll say choose. And I feel funny writing n of n as a function of natural numbers, so I'll call it tau. Let's say that the hypothesis that tau is bounded, or has a bound, has its lower bound, that n is less than capital N. And let's get the hypothesis that tau satisfies P using H. What this will introduce for us, I think I wrote it right here, is 3 things. This adds 3 things. It adds a function tau from the naturals to themselves. It adds, we called it H tau bound, which is the fact that for all capital N, tau of capital N is at least capital N. right? Because this says, this hypothesis H says, no matter what n is, I'll find a tau of that n. I'll prove to you that that tau of n is greater than n, and I'll prove to you, this is called H tau p, for all n, p of tau of n holds. Does that make sense?
Like some was asked this before with how this. That tau is a function and not.
So the reason tau is a function is because H holds for all n. So you give me any n, I have to give you a little n. That's a function from the natural to the naturals. That's exactly what we're calling tau. Does that make sense? That happened last time, but it happened quickly. So I wanted to isolate this little step. Okay, so let's try starting the proof with this. Okay, now we have our tau. We know that tau of n is greater than capital N, and we have to prove that this property holds for all those values. Where are we supposed to get this subsequence? John.
So I actually thought about this a little bit for class.
Okay.
And pretty much, yeah, so tau is from natural to natural, so what do you want to assign 0 to? It's tau of 0, right?
Okay.
And for what do you want to map 1 to? It's tau of 0.
Yep.
And you're pretty much, you just want the orbit of tau.
That's exactly right. That's exactly right. Is that the way we set up the last problem is you had a sequence that was always bounded below by y equals x, whose graph was bounded by y equals x, and you could make it strictly increasing along subsequences by iterates. That's exactly what this, is designed to do. Show me more help. You can make sigma by taking an orbit of tau. And let's start with this let statement. So let, and exactly, where do you want to start? Now, you can't start at 0. Why not? Sean? Exactly. We don't know that P of 0 is true. So just take one copy of tau, and now you know that P of tau of 0 is true, and then keep iterating tau after that. Does that make sense? Okay. So I'll write this. I guess I'll record it here. So the next line is let sigma. There's a slicker way of doing these also. I won't teach it to you right now. Sigma is a map from the naturals to the naturals, defined as a function that sends n to, you take tau iterated n times, but don't apply it at 0 because you don't know that it holds at 0. You apply it one more time. And of course, you could have written tau to the n plus 1, which is definitionally the same thing. Okay, so we have our sigma. Now, I think I said this last time. You see, you can't tell what sigma is. So whenever you do a let, it's very good right after that let to have a trivial have. So you can see what have sigma is. Whoops, sigma is. And it's the fact that for all n, sigma n is equal to tau to the n of tau 0. Then we can actually see what sigma is on the board. Why is that true? REFL, yeah, I think REFL is going to complain because there's a for all n. So let's just start with an intro n and then REFL. Okay. All right, so now we know what sigma is. Sigma is tau to the n iterated, tau iterated n times, really n plus 1 times from 0, but n times from tau. So far, so good? Okay. Our goal is to show that there's this subsequence sigma. So what do we want to do next? We've created a sequence. We've created some sequence of natural numbers sigma. Sean, use it. Right? Does that make sense? So next line is, of course, use sigma. Once we use sigma, what will our goal be? New goal. Brandon.
Say what, subsequence of sigma and for all n.
Exactly. And for all n, p of sigma of n. Okay, so then what's our next goal after that? Split the ands up. Yep. Split ands. So now we have two goals. How are we going to prove subseq sigma? Brandon?
That's the theory we just.
That's the theorem we just proved. Exactly right. That's the theorem we just proved. If I could only remember what it was called. I guess I have to zoom out to remember what the theorem was called. It was subseq of iterate. Subseq of iterate. Okay, so if we apply, I think we can just apply it directly. Apply subseq of iterate. See, I'm breaking my own rule. I'm breaking my own rule because this is a naked application of but it's so nice to be able to just write that and not have to spell out exactly what it's supposed to do. Let's see if it works. Let's do a little experiment. Okay, so there exists such a sigma, so use the sigma that we just created. We have two things, bless you, so split them up. And now is it true that apply subseq of iterate will do it? It will. Okay, so subseq of iterate, if we remember what the, maybe I should, yeah. If we remember what subseq of iterate is, yeah, I mean, it's an exact, there's a one line, oh, I see, I can't see it and be zoomed out like this, zoomed in like this. So subseq of iterate needs a sequence. It needs the fact that that sequence is always increasing and it needs a base point. I think that's the better way to do it. So what's our, instead of having a naked apply, what is the sequence? No. Sean. Tau, the thing that we're iterating, the theorem wants some sequence, sigma, and it's going to prove that the iterating function is a subsequence, and the thing that we're iterating is tau. So we want to feed it tau, not sigma. Where is the fact that tau grows at least like y equals x? Yeah, that was called h bound. It's right here. H tau bound. H tau bound. Okay. And what's our base point? N0. Tau of 0. Exactly. Our base point is tau of 0. So this is no longer a naked application because it's an application where we're spelling out all the details and we know exactly what's supposed to happen. So let's try this again. Whoops. The split ands is good. Do the split ands. Okay. So now it's just a one-liner. Apply subseq of iterate, but with what sequence? Tau is the sequence. H tau bound is the reason that it's bounded below. And then what's our base point? Tau of 0 is our base point. And that should close the goal completely. Intermediate goal closed. Okay. So now our next goal is for all n, P of sigma of n holds. We found this subsequence along which the property is always true. First step. Intro. Let's see, I'm sort of breaking my rule that I keep jumping back and forth. Okay, so this finishes that. That split gave us two things. Now we're trying to show this. So we intro n. Now our goal is, the new goal is P of sigma of n. Why is this true? Sean. Exactly. This H tau P, let's see, let me get rid of this. We have this H tau P that says for all n, P is true if it's applied to an element of tau. So we have to change. I'm all over the place. Come on, focus. Okay, so let's change the goal to say the following. Change the goal to say P of, now what is the definition of sigma? It's tau to the n applied to n. So it's actually tau to the n plus 1 of 0. That's by definition. And then once we make that change, how do we get it to say there's one tau all the way on the outside? Other than Sean, other than John. It's not good.
Rewrite myself.
Exactly. Rewrite, and let's make it not a naked rewrite. Show tau of tau to the n of 0 is equal to tau to the n plus 1 of 0. That's by apply successor iterate. And the problem is this is going to look for tau of tau to the n. It's not going to find it. So backwards. Yeah. Rewrite backwards by that. And now what do we, what's the, oh, question? Sure.
Would it be like more efficient to just rewrite using sigma is?
You could, yeah. The change and the rewrite by sigma is are doing the same thing.
Oh, because like if you use the sigma is, you don't have to deal with the n plus one stuff. Like because that's tau to the of tau of 0.
The tau is in the wrong place.
Oh,
That's why the change will work. It's definitionally equal to tau to the n plus 1. It's not definitionally equal to tau of tau to the n. So what we're doing is effectively moving one tau from the inside to the outside. Great question. Okay, that makes sense? All right. So the tau is on the outside, and now this is the new goal is P of tau to the n is 0, which is solved by Did I lose you guys? Or yeah, the new goal. So after this rewrite, the rewrite interchanges, it turns tau to the n plus 1 of 0 into tau of tau to the n of 0. So how do we prove that P of tau to the n of 0 holds? Do we have something that guarantees that P of tau of a number is always? Yeah, so it's H tau P with what value of capital N? H tau P with capital N equal to tau to the n of 0. Okay. And again, you don't need to put this. Lean will figure it out, but I would like you to for pedagogical reasons. Okay.
Like introducing sigma, you just use.
We could have said use, yes. Introducing sigma is a purely pedagogical, yeah, there's a much faster proof, which jumps straight to use, instead of use sigma, I could have said here, am I going to ruin everything? Let me try to do it in editor mode. Instead of letting this, oh no, did we lose everything else? Well, maybe we did. So instead of this, I could have just said use fun n maps to tau to the n of 0. Yeah, I guess tau is a function. So let's look back. We started with this choose to get tau, to get the function tau. So now we have the function tau, and we want to know that there exists some sequence sigma. And what I'm saying is use the function that maps n to tau to the n of 0. And it's not 0, actually, it's tau to the n of tau of 0 that I want to be here. In fact, there's no harm in just putting an n plus 1 there also. Does that make sense? Was this your question? Oh, why not just tau? Use tau. That's what this is. It's the map. The way to say tau iterated n plus 1 times starting at 0 is it's the map that sends n to tau to the n plus 1 at 0. I'm not understanding your question. Yes.
Then tau iterated n plus 1 times also.
That's right.
So why can't we just use tau?
Because
Well, how does that part?
the problem with use tau,
No, he's saying use it, just use out of that.
yeah. What is n? It's a variable in a new function that we're creating. It's not that we're going to iterate tau n plus 1 times and now have that be the function. The function is tau of tau of tau of tau, and that's the variable. Does that make sense? That's a very, very good question. I'm really glad you asked that. It's not any one of the tau iterated n plus 1 times. None of those are the function we want. It's all of them. So that's why it's a function as n goes to, maps to tau to the n plus 1, evaluated at 0. Okay, does that make sense? The reason I prefer to do a let with a sigma is so that you don't get stuff that looks like this. This is pretty ugly, right? It's this I need to prove that the function that maps n to this thing is a subsequence, and for all n, p of the function that does that it holds. It's not so nice. There's nothing wrong with it, but let's work with it. Let's work with it. So then we would split ands. Right? We split up the ands. We have to show that this thing is a subsequence, but that's exactly, so apply, what was it called? Subseq of iterate, if I've got the names right. Which sequence are we iterating? We're iterating tau. Let's see if this will work, actually. I think it should, because those two things should be definitionally equal. Subsequence of tau. The fact that tau, we need, where's this theorem? I just want to make sure I get the hypotheses in the right order. So we have tau. We need the fact that tau is always at least n. That's h tau bound. Then we need a starting point. The starting point is tau of 0. And I think it did it. All right. Now we have a for all n. So intro n. We have to prove that this thing holds. Now, all right. Maybe we can rewrite directly. And I'll even do it the fast way, suck iterate. Let's see if this will work. Nope, it didn't see through the definitions. There are too many things going on. Okay, so let's, do I have to delete that manually maybe? Okay, so let's rewrite show tau of tau to the n of 0 is equal to tau to the n plus 1, this I think will work of 0 by apply suck iterate. I think this will work because it's going to try a little harder to see if it can find tau to the n plus 1 of 0. And I think it will find it. Still no. All right, let's start with a change. Change p of tau to the n plus 1 of 0. Okay, the change it managed to do. So you see, this thing says you have this function that maps n to tau to the n of 0 at 1, and you want to evaluate that function at n. And that's just too much for it to see through with what we were doing before. Now we can do our rewrite. I'll just do the quick version, iterate. Okay, and now apply. Again, I'll do the quick version. No, let's not do the quick version. Tau to the n of 0. Okay, make sense? Brandon.
An next question, but when you have like tau to the power and then square brackets n, if you put parentheses n, that would be a different thing. Would that be like raised to the power or something?
Yeah, or differentiate n times. Yeah.
Okay.
The syntax for iterating a function is square brackets. Okay. That was all review. The next level, the next two levels are things that we covered last time. So if you're monotone and bounded, then you're Cauchy. We proved this last time. The way I'm setting it up now is that I'm saving this iterated gap. Remember, what this theorem, the negation of is Cauchy is that you'll always be able to get some gap of epsilon along some future sequence. And you want to be able to iterate those. So I saved this iterated gap theorem for last, instead of starting with the iterated gap theorem. So we'll prove monotone, if you're monotone and bounded, then you're Cauchy first. And then the next level is to prove the iterated gaps, that the gaps can actually iterate. Just pointing out to you that we've reorganized things a little bit. All right, let's jump to lecture 13, which is today. Let's get to Bolzano-Weierstrass. Okay, we need some definitions. We need some good stuff. So where are we? Last time we showed that if a sequence is monotone, and bounded implies Cauchy. This time we're going to show two things. Well, really one thing. We're going to show the following theorem. So here's the theorem. Yeah, I have to talk about peaks. Let's talk about peaks. Okay. Well, Cauchy is going to eventually apply convergence. Once we finish our conversation with... that's right.
Why is it so helpful to talk about like in terms of like,
Because in order to say that Cauchy sequences converge to a real number limit,
oh,
I have to tell you what the real numbers are. And that is, I think, what we're going to get to, not today, but tomorrow. Tomorrow being next class. Okay, so here's the situation. We want to prove Bolzano-Weierstrass, okay? So we want Bolzano-Weierstrass, bless you, which says if you're monotone, then there exists a subsequence which is Cauchy, and hence converges, which is Cauchy. Okay, so the picture in my head is you're bounded. I'm sorry, I said monotone, I meant bounded. Bounded. You have some window minus m to m, and your sequence is stuck. Whatever it's doing is doing something totally crazy. It's stuck somewhere inside this sequence. What we're trying to show, the Bolzano-Weierstrass theorem claims, is that there's always some subsequence along which the thing is Cauchy. If we could find a monotone subsequence and it was bounded, that would get us Cauchy. If we can't find a monotone subsequence, maybe we can find an anti-monotone subsequence, which would be bounded from below, which would also be Cauchy. That's your homework. Okay, so homework, let me put it here. Homework is antitone. Antitone is the opposite of monotone. In other words, non-increasing, plus bounded from below, bounded below, implies there exists a subsequence that's Cauchy. I should say here, sorry, implies Cauchy. Implies Cauchy. Okay, if you're increasing and you can't keep increasing forever, then you're Cauchy. If you're decreasing and you can't decrease forever, then you're Cauchy. And so what's left in order to prove Bolzano-Weierstrass is, so the claim is bounded implies there exists a subsequence which is either monotone or antitone. If you have a bounded sequence, then either there's always some subsequence that's increasing or some subsequence that's decreasing. Okay, so let's think about decreasing sequences. Let's think about something that we'll call peak. So is a peak. Is a peak takes a sequence, again, to either the rational numbers or the real numbers, and it takes a natural number n. And here's what is a peak is trying to represent. This is the situation. You have some sequence, it's doing, I'll just draw it as a curve. You have some sequence, and then there's a value n, so that this sequence never again exceeds this value. So forever, whatever it's doing after that, I don't care what it's doing, but I never go above this value again. Okay, so is a peak is the fact, is a prop. How is that prop defined? How would you define the fact that for all future values, so for all m greater than or equal to n, the sequence never gets above this value? Stop it. Exactly. And that's how is a peak is defined. Daniel. The backward side? Nope. Nope. It could be, yeah, it doesn't have to be a strict peak. In fact, this is also a peak. And this is also a peak. And this is also a peak. And you see, if you have infinitely many peaks, then what? So then there's a decreasing, exactly. Then there's an antitone subsequence. So that's a condition called unbounded peaks. So we say that the sequence A has unbounded peaks. Well, how did we say it for the twin prime conjecture, that there's infinitely many twin primes? There's infinitely many peaks. If Sean. Yeah. Yeah, let's say strictly greater than n.
Is a peak.
Yep. Yep. A, and so that M is a peak, okay? So no matter how far out you go, no matter what your bound N is, there's always some future value, M, so that A has a peak at M. Does that make sense? And so the easier theorem I've saved for homework, the harder theorem we're going to do together. And the harder theorem, did I give this one a name? Monotone subseq of bounded peaks. So here's our goal, our target theorem, which is called monotone subseq of bounded peaks, is the following statement. That's the name of this theorem. It's the following statement. Our objects are A, which is a sequence. So we're given A. Our assumption, HA, is that it's not true that has unbounded peaks. That's an awkward way of saying the peaks that are bounded. There's a last peak. There's going to be some point over here somewhere, which is a peak. And after that, there's no more peaks. Well, what does it mean that there's no more peaks? Suhas. Yeah, it's got to keep climbing. It has no other choice but to, there's a subsequence along which you can keep climbing. And that's exactly what the goal is. Goal is that there exists some map sigma, which is a subsequence. And if you compose A with sigma, it's monotone. Okay, that's our goal. Brandon.
Like, since you defined like it as like M.
The constant sequence has implementing peaks.
This is A and then it's less than. So like,
Yep.
that's the peaks. Okay.
And monotone and antitone are both non-strict.
Yeah.
So the constant sequence is both monotone and antitone. And has implementing peaks. Yep. Good question. Okay, does that make sense? So that's our goal. What are we going to do? How are we going to show that if there's a last peak, there's a place after which there are no more peaks? The sequence might look like this, right? It could have a peak somewhere. It could have, could have a couple of, it could have a couple of peaks, but then this is the last peak. Or maybe this is the last peak. Like it's going to keep climbing. It'll never reach this because this is a peak. That's what it means to be a peak. It'll never reach that, but it won't ever have a peak again. There's no value, n, so that all future values are at most this high. So there's some future value that's always going to get above this value. It's not going to get higher than this, whatever the last peak was, but it can still keep climbing. So that's why this is much more subtle than what you'll prove in your homework, which is antitone subsequence of unbounded peaks. If the set of peaks is unbounded, it's not that hard to prove. Here we have it's a little bit harder of an argument.
Does that mean that
Nope. Well, not necessarily, but it's a bound. It's a bound for the tail. But it's not necessarily a limit. It could keep climbing and climb to something that's not necessarily what this peak was. Daniel.
How would you motivate
Oh, how would you motivate the idea of thinking about peaks? So we're trying to see, in some sense, it's all motivated by, if you have a bounded sequence, the sequence can't go outside of minus MM. We want to know, does it have some limit does it have some subsequence that has a limit? Has a limit for us right now means is Cauchy. So if it was monotone, it'd be very easy to show. If it's monotone and bounded above, that's enough to get us to be Cauchy. If it's antitone and bounded below, then we'll get something that's Cauchy. So how do you, what would it mean for it to be monotone? How do we find some monotone subsequence? If we have these peaks, if we have infinitely many peaks, if we keep having peaks, then we can go down, 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 down. Does that make sense? And if we don't have infinitely many peaks, then there has to be a reason. Then we have to keep climbing. So it's that's kind of the motivation for thinking about things this way. But how do you actually prove this? And of course, we're going to run out of time. So let me get started. First, let's unpack what all of this means. Let's change HA to its definition. So change at HA. And what is it? It says that it's not true, has unbounded peaks. What did that mean again? Sean?
For all.
Yeah, I'll use a capital N for no reason.
Is it
Right. Is a peak AN. And what does it mean to be is a peak?
Roll.
Okay, so let's make that big change. So change, it's not true that for all big N, there exists little n after big N, so that for all m greater than or equal to little n, am is less than or equal to an at HA. Now, did I get the less than or equal to and less thans? Because there's some choice about do you want it to be less than or greater than. So let's just check. The peak has to happen after m. So that wasn't quite right. And this one also is a strict inequality. Good. I think that's going to work. Great. So now HA says it's not true that for all n, there exists little n greater than capital N, so that for all m greater than little n, A of m is less than or equal to AN. Wow, what a mouthful. What should we do next? Push through that negative sign. Yep. Push neg. And what will that turn the new HA into? There exists some largest value, n, so that for all n greater than that n, there exists some m after that n. I guess that was supposed to be a strict inequality. So that this fails, so AN is less than AM. Okay, does that make sense? So let's push neg. Of course, at HA, I should have said, at HA. Okay, so there is a last peak. There exists some value n, so that for all little n greater than that capital N, there's some m, let me draw a picture. There exists a capital N, so that for all little n, after that capital N, there's always some little m even farther along that gets higher than this value of A of n. Does that make sense? You just draw a picture, everything is clear. So there's a last peak. Okay. Well, let's get that last peak and let's work after that last peak. So how should we get that last peak? Let's choose this capital N, and then just H capital N using HA. Too many O's. All right, so now we have this HN that says for all n greater than capital N, there's going to be an M and A of n is less than A of m. What's the key idea now? Sam. Exactly. We want to define a function. This means that there's a function. So how do we define a function? We're going to get this function out of HN. Choose, it's that other use of choose. It's that more advanced use of choose. So let's choose a tau. Tau will give us a map from little n to m. M is what tau is representing. So the fact that m is greater than n, that'll be called tau bound. And the fact that A of n is less than A of tau of n will be called tau A or something. How about that? Using, this is called H capital N. Does that make sense? And here's where it's going to get complicated, and we're probably going to have to stop there. Choose tau, tau bound, tau A, using HN. Look at tau bound. So it worked. It worked. it said tau is a map that takes a natural number, insists that that natural number be greater than this last peak, then it will give us a natural number m. So it's not a function from n to n, like in our previous examples. That's why this is harder. Okay, so we're gonna have to do some work on this, but we have the condition tau bound that for any n, as long as we're past this last peak, tau of n together with a proof. See, tau doesn't take just a natural number, it takes a natural number and a proof that that natural number exceeds capital N. So tau of n together with this proof that's unnamed exceeds n. And the last condition is that for any n, as long as it's greater than capital N, we have that a has grown. So we're gonna want to take tau and iterate it, but you can't iterate it. You can't iterate it because it's not a map from the naturals to the naturals. Every single time you apply it, you have to give a new proof that n is greater than capital N. Okay. So we have to invent some new techniques to be able to handle this. And that's what we're gonna pick up next time.